Hello, Year 11s. I'm Mr. Noor. I'm going to be taking your lesson today on pressure, which is specifically to do with pressure in fluids and upthrust. So take down the title and the date, and then we'll continue. So pressure in fluids and upthrust, great. So can you explain why an object will float or sink? Just pause the video and take a shot, a guess at this. So an object with the greatest density, and we know density is mass over volume. So if it has a greater density, then the liquid or gas it is in, it will sink. So for example, a boat, if its density is greater than that of the water beneath it, it will start to sink. And an object will float if its density is less than the liquid or gas which it is in. So these are our lesson objectives today. Quickly note these down. So we have to explain atmospheric pressure, which is important to know because we can predict weather patterns from this, then explain pressure with depth and density, which is also important. As we see in sort of submarines, we don't want them to start collapsing on themselves once they're underwater. And finally, defining upthrust as the weight of the fluid displaced. So that is effectively the fundamentals of buoyancy and how things float in water or liquids. So quickly to start, let's do a starter of the circles. Let's put pressure in the middle and just list as many key terms as you can about pressure. Pause the video now and take 2 minutes on that. Any key terms you can get to do with pressure. Great, well done. I hope you got at least sort of 5 or 6 terms there. But yeah, you might remember pressures to do with sort of force, force on an area, or feeling pressure or atmospheric pressure or anything to do with the atmosphere, or things like that. So well done for doing that. Let's move on to define what pressure is with an equation. So pressure is the force applied over the area, the surface area. So for example, if you had a table, pretend this is a table here, my hand is applying force downwards on the table, and the area is which my hand is in contact with the table with. So force applied over the area, which it's applied to, and that is the pressure, the downwards pressure of my hand on the table on the book. So make a note of that equation. Pressure equals force over area, and that is in newtons over per meter squared. But actually, we call that pascals. So we measure pressure in pascals, which is the same as newtons per meter squared. So atmospheric pressure. We have an atmosphere, and there is an atmospheric pressure of all the air particles pushing down on the Earth. So, for example, the air particles around you right now are pushing down on you due to gravity, forcing them down onto you, which is creating a pressure. So atmospheric pressure is just the air pressing down due to gravity. And so you can see on this diagram on the screen, the nearer to sea level or the lower down you are, the higher the pressure will be, and the higher up you are. So for example, at the top of the mountain, there'll be less air pressure, lower air pressure. And that's due to less density of air particles. So near sea level, there's a higher density of particles, and that results in a higher pressure because more particles forcing down on you. Whereas if you're higher up, for example, up a mountain or in a helicopter or something, there'll be less air pressure due to less particles around you pressing onto you or onto an object. So there's lower pressure near sea level and higher pressure near sea level and lower pressure further up in the Earth's atmosphere. So you can see here, note down quickly, at 100,000 feet, the air pressure, the atmospheric pressure is going to be about 1.12 kilopascals. At about 20,000 feet, it's going to be 46.61 kilopascals. And the one you probably need to remember is at sea level, which is what we use for our calculations generally. The atmospheric pressure is 101.325 kilopascals, around 100 kilopascals. So make note of that. So you can see atmospheric pressure and in use here. This is a weather map, a weather forecast chart. and you can see the pressures labeled on there with little X's and numbers next to them. And we can determine now, by measuring these pressures, what type of weather is due, or what weather fronts are moving in which directions. And so when you have a low pressure, you usually are going to have an unsettled weather, perhaps clouds and rain. So you have wind coming into this low pressure zone, and that is meeting air particles which are rising upwards, and that in turn creates clouds and often rain and unsettled weather. Whereas if you're a high pressure zone, you are going to usually have more settled, calmer weather, less cloudy. And so you can sort of see these weather fronts moving and determine sort of how hot or cold or what weather will occur depending on the atmospheric pressure. So it's very useful in day-to-day life. Great, moving on. So can you calculate the mass of air currently pushing down on you? So pause the video, take a couple of minutes, remember the equation you used, and see if you can calculate the mass of the air which is pushing down on you. Great, so hopefully you had a good little go at that. If we continue, we know pressure is force over area, so the force applied over the surface area. And we know that the force of the air on us is going to be the mass times gravity, because we know that it's the gravity pushing on the air particles pushing into us. So mass times gravity over area. And to find mass, we need to rearrange that. So we bring area across and multiply that by pressure. We multiply both sides by area, and then you divide by gravity, and then you get mass by itself. And if we put in the atmospheric pressure at sea level at 101,325, times that by 0.5 times 0.2, and divide that by 10. So you're taking, half a meter, sorry, not half a meter. You're taking mass, we're taking pressure, and we're timesing that by the area. So around 0.5 meters by 0.2 meters. And then dividing that totally by gravity, which gives you 1,013 kilograms of air, which is a lot, but we're not really feeling it much, are we? And so the area, 0.5 times 0.2, is, the rough sizing of a school pupil, isn't it? So moving on. So think about this practically. What about increase or decrease in air pressure? What effect could that have in life? So, for example, if you have a boat on water, if the air pressure is increased above the water, that will push down on the sea and actually lower sea level. So you see the boat is sitting closer to the bottom of the water there. So you can see the rocks down there. So if the air pressure is increased, the water levels will actually drop. Whereas if you reduce the air pressure, the water levels will rise up slightly. And so air pressure actually has an effect on the seas, and which can result, you don't want to crash your boat or ground your boat along the bottom of the sea or bottom of the lake. So if the air pressure is specifically high, it will mean you're more likely to run along the ground in your boat. So it actually has an effect on the seas, this atmospheric pressure or the air pressure. So now if we look at pressure in a liquid, if you underline this in your, create a little title in your books, pressure in a liquid, effectively within a liquid, the deeper down you go, the greater the pressure, because the more, for example, if we're taking the sea, the deeper you go in underwater, the more water you have pushing down on you. There's a greater volume of water pushing down on you. So effectively, it's the deeper you go, is the greater the pressure. But if we put that into an equation, pressure is going to equal the depth, so how deep you are, times by the density of the water, the liquid, whatever it may be. So the depth you are times by the liquid density times by gravity, because that's forcing it down onto you. It's similar to air pressure. Gravity is forcing the liquid down onto you, and the density of the water matters, and how deep you are affects. So the greater depth you are, the more pressure you're going to feel. So calculate the pressure on the submarine, which is 250 meters underwater, if the water density is 1,025 kilograms per meters cubed. So remembering the equation you just learned, pause the video. Using the equation you've just noted down, you should be able to calculate this with the given units here. Great, so moving on, we've got pressure is equal depth times density times gravity. So the pressure is going to equal, it's written down in the slide there wrong. It should be 150 meters times 1,125 times 10, and that will give you that answer there. Fantastic. Upthrust. So now we're going to look at upthrust, and what keeps us afloat. So if you're a boat on water, as you can see on the right there, simple boat on water, what keeps us floating? And that is buoyancy, it could be called, or upthrust. So upthrust is equal to the weight of the displaced water. So if you have something sat in the water which is being moved out the way beneath it, because a boat doesn't sit perfectly on the top of the water, it sinks down, but the water which has been moved aside by the boat is equal to the upthrust. So the weight of the displaced liquid is equal to upthrust. And so how do we find the weight of a displaced liquid? There you go. So upthrust is equal to the weight of displaced liquid. So how do we find that? We do volume times density times gravity. So we know that weight is mass times gravity, and we can find the mass by using, the equation of mass is equal to volume times density. So we sub that in, and then we have upthrust is equal to the weight of the displaced liquid, which is going to be volume times density times gravity. So make a note of that. And here you can see on this boat, we have the weight of the boat going down, and we have an equal and opposite reaction of upthrust of buoyancy. So, for example, Mr. Gregson has his big yacht. His boat is 18 meters long and 4.5 meters wide, and the bottom of the boat is 1.2 meters below the surface of the seawater. And we're taking the seawater density as 1,025 kilograms per meters cubed. So calculate the mass of the boat. So using the equation you've just seen, can you calculate the mass of the boat? Pause the video and take a go. Fantastic. So here we go. Correct the mistakes you've made in your book with purple pen. The volume of the boat is going to be 18 meters long times 4.5 meters wide times 1.2 meters deep. So that's how deep it is in the water. And that is going to equal 97.2 meters cubed. And so therefore, the displaced water, which is equal to the upthrust, is going to be 97.2 times 1,025. And then you'd actually times that by 10 for gravity. But to find the mass, we're going to have to divide by gravity, which is dividing by 10. So they cancel each other out. So effectively, you can leave their gravity out there because we're trying to find the mass. So we're going to have to divide by gravity at the end anyway. So that should get you 99,630 kilograms is the mass of Mr. Gregson's boat. There you go. So there's the explanation. I could have times by 10 for gravity and then divided by 10 to find the mass, but there's no need. Great. So let's recap calculating density. So we know density is mass over volume. So we used that earlier. Mass equals density times volume, but we rearranged it. So here we have density is equal to mass over volume. So for a boat, 10 meters long by 5 meters wide by 2 meters high, what is its volume? Quickly note that down. See if you can pause the video and calculate that. Great, so you should have times them all together. So that should be what 100 meters cubed for your boat density, volume, your boat volume. And then if we use the same boat with that same volume, what will the density be if it's made from a 7,000 kilogram, 7-ton steel container? So what will that be? So what will the density be? We divide the mass by the volume. So it's going to be 7,000 divided by 100, which is 700 kilograms per meters cubed. And then with the same boat, sorry, my face is in the way. With the same boat, if it starts to flood, so if there's water getting over the sides, how much water required to increase the container density to 1,000 kilograms per meters cubed? And what's going to happen once it reaches that point? So pause the video. Great, fantastic. So with that calculation, once you've reached 1,000 kilograms meters cubed, that is the same density as water. So what's going to happen to your boat when your density of the water and the density of the boat is the same or greater than the density of water, the boat is going to start sinking. Fantastic. So there will not be enough upthrust to keep that boat aloft because the density of the boat is higher than the density of the water. Fantastic. So that's a quick recap with density, but today you've been learning about pressure. So we've done atmospheric pressure, we've done pressure and depth and density, and then we've looked at upthrust and buoyancy with liquids. So you should be able to add them all to your revision notes and complete those questions. Make sure you have those corrections in, and have a good day.